Okay, hi everyone. In the first lecture of the phase rule, we have discussed the basic definition which are useful in the phase rule, such as system, phase, component, and degrees of freedom. So here in this lecture, we are going to discuss the equilibrium, types of equilibrium, then chemical potential, and derivation of the phase rule. So here first of all we are going to discuss the term chemical potential. So the chemical potential, it is denoted by symbol mu. So here the partial molar Gibbs free energy has been given a specific symbol mu because of its universality in dealing with the various aspects of the thermodynamic study. So here this chemical potential, it is denoted by symbol mu. So here definition of the chemical potential. So chemical potential is defined as the change in free energy of the system produced on addition of 1 mole of the substance at constant temperature and pressure to large bulk of mixture so that its composition does not undergo any change. So friends, this is the definition of the chemical potential. So all of you know that the free energy, it is denoted by symbol G. So here chemical potential is defined as the change in free energy of the system produced on addition of 1 mole of the substance. So here at that time the temperature and pressure it is considered as a constant. So here it is denoted by symbol mu, and mathematically the chemical potential, it is given by the equation mu is equal to delta G by delta Ni. So here the delta G, that is a change in free energy with respect to number of moles of the ith component when the temperature, pressure, then number of moles of the first component, number of moles of the second components are constant. So here this is the mathematical definition of the chemical potential, that is the mu is equal to delta G by delta Ni at constant temperature, pressure, number of moles of the first component, number of moles of the second component, and so on. So here this chemical potential, it is also denoted as symbol Gi. So here this is the definition of the chemical potential, and here what is important, chemical potential, it is the intensive property. So here at equilibrium, the chemical potential of the substance in the system must have the same value throughout the system. That's why here it is the intensive property. So here this is the definition of the chemical potential. Then the second point is the phase diagrams. So here in this chapter we are going to consider the one component system as well as the two component system, and we are going to discuss the phase diagrams for one component as well as for the two component systems. So let us consider what is the phase diagram. So here the phase diagrams are the graph showing interdependence of variable, and here with the help of these graphs the coexistence of the different phases in polyphase system can be studied. So here for one component system, how the phase diagram is constructed. So the phase diagram is constructed by plotting the pressures and temperature of all the possible phases. So in case of the one component system, so all of you know that in one component system C is equal to 1, but in case of the two component system where C is equal to 2, the phase diagrams are constructed by plotting composition of each phase against temperature at constant pressure. So here in this way we can construct the phase diagrams for the one component as well as the for the two component system. Then here the next point is the equilibrium. So here existence of various phases leads to attainment of equilibrium among themselves. So here heterogeneous systems involve three types of the equilibrium. In phase rule we are going to discuss, or we are going to consider the heterogeneous system. So all of you know that in the heterogeneous system that is there are more than one phases. Such a system, it is called the heterogeneous system. So here the equilibrium involved in the heterogeneous system, there are three types such as the stable equilibrium, then metastable equilibrium, and unstable equilibrium. So here this stable equilibrium, it is also called as the true equilibrium. So let us consider one by one. So, the first one is the true or the stable equilibrium. So, here the state of the system at which different phases of the same substances are stable and in equilibrium irrespective of the direction of the attainment of the state is called as the stable or the true equilibrium. So, here true equilibrium is attained when the free energy content of the system is at the minimum for the given values of the variable. So, here an instant of such equilibrium is ice and liquid water. So, here the equilibrium between the ice and the water at 1 atmospheric pressure and 0 degree Celsius. So, here at the given pressure, the temperature at which the two phases are in equilibrium is same whether it is attained by the partial melting of the ice or partial freezing of the water. So, here when the ice is equilibrium with the liquid water, this is the example of the true or the stable equilibrium at 1 atmospheric pressure and 0 degree Celsius. So, here this is the first type of the equilibrium, true or the stable equilibrium. Then the second one is the metastable equilibrium. The equilibrium which is highly unstable and which possesses the tendency being changed to true or stable equilibrium is called as the metastable equilibrium. So, here let us consider one example, that is the water at -5 degrees Celsius. So, all of you know that it is possible to maintain the water in the liquid state below 0 degrees Celsius, and such water it is called as the supercooled water. So, here the water at -5 degrees Celsius can be obtained by careful cooling of the liquid, but not by fusion of the ice. So, here water at -5 degrees Celsius is said to be a state of metastable equilibrium. So, such equilibrium is attainable only under the particular condition, that is in one direction only. So, here when we consider the water at -5 degrees Celsius, and here as soon as a small amount of the crystal of ice is introduced in the water at -5 degrees Celsius, or small amount or the liquid is just touched. So, here immediately the solidification sets in rapidly and the temperature rises to 0 degree Celsius. So, here such a water, it is a supercooled water, and such equilibrium it is called as the metastable equilibrium. So, once again the equilibrium which is highly unstable and which possesses the tendency of being changed to true or the stable equilibrium is called as the metastable equilibrium. So, here when we consider the supercooled water at -5 degrees Celsius, when we add the small amount of the ice in such water, or when we just touch the supercooled water, immediately the solidification takes place, and here the metastable equilibrium it is converted into the stable equilibrium. So, this is the second type. Then the third type, unstable equilibrium. A state of unstable equilibrium is said to exist when the approach to equilibrium in a system is so slow that the system appears to undergo no change with time is called as the unstable equilibrium. So, let us consider one example here just to understand what is my unstable equilibrium. So, here when potassium chloride added to water, all of you know that the potassium chloride is soluble in the water. So, it dissolves and clear solution is obtained, indicating that equilibrium has been attained. But the addition of the salt continue to dissolve till the state of the saturation has been established. So, here in the water if we add the potassium chloride, so it dissolve in the water, and finally here the state of the saturation has been established, whereas actually the process is still proceeding very slowly toward the true saturation. Such a equilibrium is said to be the unstable equilibrium. So, here friends, when we consider the equilibrium, there are three types of the equilibrium: stable equilibrium, metastable equilibrium, and the unstable equilibrium. Then the next point is derivation of the phase rule. So, here how the phase rule is derived, or what is the equation for the phase rule, mathematical equation for the phase rule. So, here derivation of the phase rule. The derivation is based on the simple thermodynamic principle that at equilibrium the chemical potential of a particular component and total phases that can be present because of the component C are P in number. So, here the P is the total number of phases present in the system. So, here every state of the system will be defined by the three variable. So which are these three variable? These three variables are temperature, pressure and the concentration. So here the every state of the system, it is defined with the help of these three variable, temperature, pressure and the concentration. So for the knowledge of the composition of each phase, it is necessary that the concentration of, that is a C minus 1 component must be known. So here, because when the total concentration, that is the C, is known, the total concentration minus the sum of the concentration of C minus 1 component gives the concentration of the remaining component. So here, as the number of phases are P in the system, the total number of concentration variables will be P in bracket C minus 1. This is very important. So as the number of phases are P, the total number of concentration variable will be P in bracket C minus 1. So in addition to these, the pressure and temperature are the two more variable. So therefore the total number of variables are, that is a P in bracket C minus 1 plus 2. So plus 2 means these two variable, that is a pressure and the temperature. So therefore the total number of variables are P in bracket C minus 1 bracket complete plus 2. This is the equation number 1. Now chemical potential automatically fix some of the variables from above equation. These are as if known variables. So here their numbers can be calculated as suppose there are three components designated by 1, 2, 3 present in 4 phases A, B, C, D in equilibrium. So here the phase equilibria is, that is a phase A is equilibrium with the phase B, phase B is equilibrium with the phase C and the phase C is equilibrium with the phase D. So for first component, its chemical potential in this phase will be, so here for the component number 1, the chemical potential of this phase phases will be given mu1 A, that is a chemical potential for the first component for the phase A. Then here the mu1 B, chemical potential for the first component for the phase B. Similar way mu1 C and the mu1 D. But at equilibrium, these chemical potentials are equal. So here the mu1 A is equal to mu1 B is equal to mu1 C is equal to mu1 D. So here, as there are 4 phases, there will be the 3 equation. So the first equation, mu1 A is equal to mu1 B. Then here mu1 B is equal to mu1 C and here the mu1 C is equal to mu1 D. This is for first component. Similar way we can write for the second component as well as the third component. So for the similar types of the equations are possible for the other component. Let us consider for the second component. So here the same equation we can write mu2 A is equal to mu2 B. Then here the mu2 B is equal to mu2 C and here the mu2 C is equal to mu2 D. This is for the second component. Then for the third component, mu2 A is equal to mu3 B, mu3 B is equal to mu3 B is equal to mu3 C and here the mu3 C is equal to mu3 D. So here if there are 3 phases, there will be the 2 equation for each component. If there are 4 phases, there will be the 3 equation for the each component. So here in general for each component in the P phases, that is a P minus 1 equation will be there. So here therefore there are C components and P phases, then the total number of equations or the variables will be the C in bracket P minus 1. So here number of variables automatically fixed, that total number of variables are, it is given by the equation is equal to C in bracket P minus 1. This is the equation number 2. So here actual number of variable required is known by subtracting equation 2 from the equation 1. So here the actual number of variable required to be fixed, that is the number of variables required minus number of variable automatically fixed. So here the number of variables are required, that is P in bracket C minus 1 plus 2 minus number of variable automatically fixed, that is a C in bracket P minus 1. So, here when we solve this, here we get the equation, that is the actual number of variables required to be fixed, that is a C minus P plus 2. This is the equation number 3. But here all of you know that actual number of variables required to be fixed is nothing but the degree of freedom, and it is denoted by symbol F. So, here equation 3 can be written as F is equal to C minus P plus 2. So, friends, this is the mathematical equation or mathematical derivation for the phase rule, that is F is equal to C minus P plus 2. F is the degree of freedom, C is the number of component, and P is the phases. So, here this is the derivation or equation for the phase rule. So, let us consider some numericals. So, the first one is evaluate P, C and F for the mixture of 5 gases enclosed in the cylinder. If the 5 gases are enclosed in the cylinder, what is the value of the P, C and F? So, here we know that gases are mixed completely. So, here the number of phases will be 1. When the 5 gases they are mixed in a cylinder, the total number of phases will be 1, even though there are 5 gases. So, P is equal to 1. So, these are the different gases, that is a 5 independent chemical species. Hence, the number of component will be the 5. Then here we can say that C is equal to 5 by applying the phase rule. What is the equation for the phase rule? F is equal to C minus P plus 2. So, just substitute the value of the C and P, here we can find out the degree of freedom. So, here F is equal to C minus P plus 2, C, that is the total number of component, that is equal to 5, and here the P. So, here P is equal to 1. So, 5 minus 1 plus 2, it is equal to 6. So, here hence degree of freedom will be 6. So, here when the 5 gases they are enclosed in the cylinder, degree of freedom it will be equal to 6. This is the first example. Let us consider the second example. Calculate P, C and F when solid carbon, then carbon monoxide, carbon dioxide and oxygen are in equilibrium. So, here the gases carbon dioxide, carbon monoxide and oxygen will make one phase. So, here because the mixture is, they mix completely. So, here the mixture of the carbon dioxide gases, carbon monoxide and oxygen, here the phase it is equal to 1. Then solid carbon will be the other phase. So, what are the total number of phases? P is equal to 1 plus 1, that is equal to 2. So, there are only 2 chemical independent species, which is the carbon and the oxygen. So, here when we consider the carbon, carbon monoxide, carbon dioxide as well as the oxygen. So, here there are only 2 chemical independent species such as the carbon and oxygen. So, the composition of all the phases can be expressed in terms of carbon and oxygen. So, the number of components are 2, that is why C is equal to 2. So, substituting the value of the P is equal to 2 as well as the C is equal to 2 in the expression for the phase rule, F is equal to C minus P plus 2. So, here 2 minus 2 plus 2 and F is equal to 2, that is the degree of freedom, it is equal to 2. Then the third example, determine the number of degrees of freedom in each of the following system. So, there are 2 examples. Water is in equilibrium with the water vapor. This is the first example. Second one is the water is in equilibrium with the water vapor. Same example, but at fixed pressure, that is a 1 atmospheric pressure. So, here in the first case water is in equilibrium with the water vapor. So, here number of component, that is the C is equal to 1, because the water and water vapor chemically they are H2O. So, here the C is equal to 1 and here water it is in the liquid state, here water vapor, that is why the P is equal to 2. So, here F is equal to, just substituting the value, F is equal to 1 minus 2 plus 2, it is equal to 1, that is the degree of freedom, it is equal to 1. So, that is only one variable, either temperature or pressure need to be specified when the water is in equilibrium with the water vapor. This is the first case. Then let us consider the second case, water is in equilibrium with the water vapor at 1 atmospheric pressure. Since the pressure is held constant, because here the pressure is fixed and it is given as 1 atmosphere pressure. So, here since the pressure is held is a constant, the degree of freedom reduces by 1. Hence, phase rule equation becomes F is equal to C minus P plus 1. So, here in this case C is equal to 1 and P is equal to 2. So, here F is equal to 1 minus 2 plus 1 is equal to 0. So, the system under the given condition is invariant, that is it is a 0 variant system. F is equal to 0 when water is equilibrium with the water vapor and at 1 atmospheric pressure. So, here these are the some numerical or some examples related to the phase rule. So, friends, In this lecture, we have discussed the first term, that is the chemical potential, then the second one is the phase diagram, then equilibrium. So, types of the equilibrium and derivation of the phase rule. Thank you.